Hi, for our presentation we will be solving problem 5-40 from our textbook. The problem reads, soil pressure acting on the concrete retaining wall is represented as a loading per foot length of wall, which is represented by this distributed load. If concrete has a specific weight of 150 pounds per cubic foot, determine the magnitudes of the soil distribution, W1 and W2, and the frictional force F for equilibrium.
Okay, so Scott just explained the general problem, so I'm just going to go through the basic premise as to how to solve it. So basically we have the concrete retaining wall here, and then there's two distributed loads. So the first form of attack is to take this triangular distributed load here and calculate that against the frictional force F, and that will allow you to find F. The next part is to come down here, and for this distributed load is to break it up into two distributed loads, the top part being a uniform rectangular load and the bottom one being like the distributed load over here. So I make a little blob. And then you can break the concrete retaining wall into two equal parts, so you can have the rectangular side over here and the triangular side. Since we still have two unknowns left in W1 and W2, getting the sum of the forces in the y direction and getting the moment around point B will give you two equations, and then with two unknowns you can solve for F, W1, and W2. Alright, so to begin our problem, we're going to sum the forces in the x direction. So that's taking the frictional force given here and equating it to the distributed load on the right side. So the frictional force is acting in the positive x direction, so that's why the F has a positive. And the distributed load is acting in the negative direction, indicated by the negative sign. And since the distributed load is acting in a triangle, it's going to be 1/2 times 200, which is our given force value, times 12, which is the distance. And equating the two is going to be F equals 1/2 times 200 times 12, giving us a frictional value of 1200.
Next, we need to find the value for the distributed load on the bottom. So in order to do that, we need to first break it up into two sections, one being a rectangle, one being a triangle. The top section, we can find its value by multiplying the length, which is 6, times its height, which is W1. For the second one, since it's a triangle, it is 1/2 times the base times the height, which is W2 minus W1. So when we simplify that, we get 3 times W2 minus W1.
Okay, so the next step of the problem is calculating the area and the weight of the soil. So you can break the trapezoid up into two parts, Q being the triangle and P being the rectangle. The area of Q, since it's a triangle, is 1/2 base times height, so it's going to be 1/2 times 4, since the length of the bottom is 6 and the upper length is 2. And then you can multiply that by 12 to get an area of 24. The area of P is going to be 2 times 12, which is also 24. The specific weight of the soil, which is given in the problem, is 150 pounds per cubic foot. So multiplying 150 times 48, which is our two areas, gives you a total value of 7,200 pounds.
So now we can continue with trying to solve for W1 and W2. We'll need a set of a system of equations. The first equation will come from, now that we have everything we need, we can do a sum of the forces in the y direction. So W1 and W2, that whole distributed load, acts in the positive y direction, so their values will be positive, while the weight of the soil, which is the 7,200 pounds, acts in the negative y direction, so that it's negative. So you can then set that equation up, which when you fully simplify it, you get W1 plus W2 equals 2,400, and that will be the first equation used in the system of equations.
Okay, so Scott just found the first equation for our systems of equations, and since we have W2 and W1, we need a second equation. So we can do that by getting the moment around point B, which is right there. So to start off, we're going to use the distributed load over here, and we found the F equivalent force to be 1200. And since it is working in a triangle, you're going to do 1/3 from the largest side of the triangle, so 1/3 of 12 is 4. So that's 1200 times 4, and since the force is working in the counterclockwise direction, you know that that is going to have a positive value. Okay, so next we're going to figure out W1 here. So since that was working in a rectangular distributed load, it's going to be W1 times the length, which is 6, and then to find the distance that the equivalent force is working from B, since it is a rectangle, it's 1/2 times the length, which is 6, which equates to the distance being 3. So it's going to be 6 times W1 times 3, and since the equivalent force is working in the clockwise direction, that's going to have a negative value. Okay, so next to find the force of W2 minus W1, since it was working in a triangular distributed load, you're going to do 1/2 base times height, so it's going to be 1/2 times 6 times W2 minus W1. So 1/2 times 6 is 3, so 3 times W2 minus W1. And then to find the distance that W2 minus W1 is working from B, you do 1/3 of the larger side of the triangle, so 1/3 times 6 is 2. Okay, so next for the value of Q and the distance that it's working from B, since it is a triangle, you do 1/3 of the largest side, so 1/3 times 4, and then you're going to add 2 for the entire portion of P, so it's going to be 4/3 plus 2, which is 10/3, so 3600 times 10/3. And then for P, since that is also working in the counterclockwise direction, that's going to have a positive value, and you're going to take 1/2 of 2, which is 1, so it's just the magnitude, which is 3600. Simplifying all of that is going to be 12W1 plus 6W2 equals 20,400.
So now that we have our two equations, the first one being the one that I discussed when we did the sum of the forces in the y, W1 plus W2 equals 2,400, and the second equation coming from the sum of the moments, which Pat just explained, which was 12W1 plus 6W2 equals 20,400. Now, that sets up the system of equations that you need. You have two unknowns, two equations, so you can solve those out, and you get that W1 equals 1,000 pounds, W2 equals 1,400 pounds, and then this was us just once again writing that the force of friction was 1,200 pounds, and that is the three values that you need to solve this problem.